In this lecture, let us talk about noise in communication system. Okay, so how your communication system behaves in the presence of noise. So, the last semester we had a course called Probability Theory and Random Processes. So, in that course, we had studied about the random processes in detail. I mean, how do we characterize the random processes, and how do we characterize the random signals. We are now ready to take up our main theme in communication systems. Okay, so we have studied several modulation schemes by now. So linear modulation schemes, as well as non-linear modulation schemes. When I say non-linear modulation, the example is FM system and PM system. Linear modulations, AM system. So we have seen pros and cons of linear modulation and pros and cons of non-linear modulation. Okay, like the pros and cons in terms of system complexity and bandwidth, etc. Okay, so we have also seen their important properties in the presence of sinusoidal interferences, like a single tone interference. Okay, like your received decided signal is cos of omega ct plus phi of t, but due to the interference you will receive cos of omega c plus omega I t plus phi of t. So this is my interference component. Okay, so this is sinusoidal interference component. However, what are the main problems in communication? It is the presence of noise. So noise is the main problem in communication. As I mentioned several times in this course, noise is one of the dens of a communication engineer. Okay, it is one of the main dens. So whatever you do, you have to keep that in mind. You have to keep noise in your mind, because noise is present right from the point at which you are generating the signal for transmission through the process that you do at the transmitter. Then it keeps on getting added while the signal is getting transmitted to the channel. You have the transmitter or modulator, then your message signal m of t, and here also the noise is getting added. The moment you put the channel, and here also noise is getting added, and then you receive at the demodulator at the receiver, and here also noise is getting added. So the noise is keeps on getting added while the signal is getting transmitted to the channel. And most importantly, because the signal is already very weak, right, when you receive at the receiver. Okay, so at the receiver, whatever noise gets added is one of the most important components of the noise. Because let's say the signal travels 10 kilometer. Now here at the demodulator, I mean at the receiver, here Rx denotes receiver and Tx denotes the transmitter, right? At the receiver, your signal strength will be very less compared to the transmitter. The moment you transmit here, signal strength will be good. Strength will be good. But here signal strength at the receiver will be weak. Okay, it's not that much good. So therefore, the noise getting added the receiver is very, very important for us. The most important component. Here the signal strength is very good, therefore the noise can be negligibly small. When I say the voltage is, let's say, 5 volt, At the transmitter, then noise may be in terms of millivolts, so no need to worry about that. But at the receiver, your received voltage also will be in terms of let's say 50 millivolts, and the signal also around 10 millivolts, comparable. So that is the problem. Okay, so at the receiver, the signals and the noise now are more or less at about the same level. That means very similar level. So whereas at the transmitter, whatever noise gets added is much smaller than the signal power. Okay. One minute. Okay, let us continue. So at the transmitter, whatever noise getting added is much smaller than the signal power. Okay, because at the transmitter your signal strength will be much higher. So therefore the noise which is getting added in the at the transmitter is not important. So the noise that is added during the transmission through the channel, and more importantly the one that gets added at the receiver itself, is the one which really affects your system very significantly in terms of your system performance. Therefore we will consider this noise which is added to the channel and the noise which is added to the demodulator. These two are important as far as the system performance is concerned, but this one is not very important. No need to consider that much at the transmitter. So what you like to now study is how do these various modulation schemes like linear modulation schemes and non-linear modulation schemes that we have discussed compare with each other in the presence of noise, because we need to figure out which system is better and which system is not good, at what condition, and how the noise will affect the system performance. So these are the questions that comes in our mind and we need to answer it. Okay, and which is better than the other. So we like to answer these questions. Now we are in the business of comparing the various modulation schemes. Okay, now we have the tools also that are required to carry out this analysis. Okay, so the tools we learned in our course, random processes, probability theory and random processes. So we will use those tools. So we know how to model the noise. Okay, once we know how to model the noise, we can analyze the performance of the system through which noise as well as signals which are getting processed. So we should know how to mathematically model the noise. So that is our objective for the next few lectures. Okay, what is the performance of various modulation schemes? So probably in this lecture let us talk about the performance of baseband system, and then the next lecture we will talk about DSB, SA system, and then AM systems, FM systems, and so on and so forth. Okay, to start with, let us look at the model that we have used for communication system. Okay, so you start with the message signal m of t, and then this m of t is given to the transmitter. Okay, so like we have pre-emphasis filter in the FM transmitter, they could be a modulator. Okay, so you can have pre-emphasis filter, you can have modulator, right? So even the transmitter contains a power amplifier before it is going to be transmitted into the channel. Okay, so then the transmitter output is getting transmitted through the some physical channel. Okay, so it is transmitted to channel. Right, so here the physical channel could be a pair of wires, or it could be wireless transmission, it could be optical fiber, or it could be coaxial cable, and so on and so forth. So the physical channel could be anything. Okay, so the physical channel could take any of this one. Now we can also model these channels. So far as the channel was an entity which could modify the spectrum of the signal, right? So you have to take a coaxial cable, you give some signal m of t, or let us say some x of t, and then you will get something in the output. That output is let us say this is a times x of t, output will be a dash times x of some t minus t naught, some delay. Therefore the channel modifies the signal in certain way. Okay, so the channel can be modeled as a certain kind of filter. Okay, because it is modifying the spectrum of the signal. Certain frequency component will be amplified and a certain frequency not amplified, certain frequency components amplitude is attenuated, certain frequency components amplitude is more attenuated. These are the kind of things will be introduced by your channel, and of course there will be certainly delay. So that's how the channel is modeled. Now in the channel the noise is getting added, so let me denote n of t. Okay, so the next component is noise. Here channel is an entity which could modify the spectrum of the signal in terms of some transfer function. Okay, so we could assume that there is a kind of linear filter, it could modify the spectrum of the transmitted signal. Okay, so in the beginning of this course we had established the conditions under which these modifications would be acceptable. Okay, we had certain kind of argument for the channel, like when we can say the channel is a distortionless channel, the attenuation is constant for all the frequencies and there is a linear delay. Okay, that is we had established. Okay, so the amplitude response should be flat across the bandwidth of the signal. The phase response should be linear across the bandwidth of the signal. If you recall, it would be like this. If you recall, minus b to b, this is flat for magnitude, and this one is phase response. So phase response is linear and the magnitude response is flat. So far we have modeled the channel like that. Now we also consider the noise gets added in the channel. So this is called a channel noise. So here n of t denotes channel noise. And a very important point to note down here is as follows. As I said in the beginning of this lecture, a lot of noise gets added at the receiver itself. So let's say I have receiver noise, the noise getting added at the receiver noise. Receiver noise. Similarly, some amount of noise is added at the transmitter itself. Transmitter noise. And also you have the noise N of t is added due from the channel. In the literature, generally what they will do is they will add all this noise together, N R of t plus N suffix transmitter noise plus N of t. This all together is called channel noise. What I mean is, even the noise is added in the transmitter block. See, the noise is added here, N suffix t of t, and afterwards you have receiver. Here also the noise is getting added, N suffix R of t. Now this N suffix R of t and N suffix t of t and this N of t all are added together, and that will be represented by N of t again. Okay, don't get confused. So your channel noise, transmitter noise and receiver noise, everything is added together, and that will be dictated, that will be shown in the figure in this place. Even though the noise is added at the transmitter, but in the pictorial representation or in the mathematical formulation, we bring this noise to this place, and the noise which is added at the receiver, that also we bring to this place in this figure. So that is how the noise is modeled. Okay, so not all noises are getting added in the channel, right? Some noises are getting added at the receiver itself, and some noises are adding at the transmitter itself. Okay, however, for the purpose of our modeling, it's purely for mathematical modeling, we show that the noises as getting added just at the input of the receiver. Okay, where is my input? Receiver, this is my input. Input to the receiver. So my transmitter noise, receiver noise and channel noise all are added in this place before the receiver. Okay, so that is, we are clubbing all the noise together. So that means whatever happens in the system, but we will blame the channel as the culprit. Okay, so this all together is called channel noise, receiver noise, transmitter noise and channel noise together is called channel noise. Okay, whether the noise gets added at the transmitter, whether it is getting added in the receiver, whether it is getting added at the channel itself, all of them are clubbed together. Not only here, in the next semester you will be studying a course called digital communication, and afterwards you will be studying a course called wireless communication. So everywhere this kind of assumption we will make. Okay, so all are clubbed together for the purpose of modeling the effect. Only for this kind of things we are doing, only for what is the reason? Modeling the noise effect. Okay, and we are saying all of them are getting clubbed together for the purpose of modeling the effect, and we are saying that the total amount of noise which is present, and that is added to the incoming channel. Therefore you have transmitter followed by channel, right? Channel, you put an adder here, it is my channel noise. When I say channel noise means it contains not only the channel noise, but also it contains the noise at the receiver, the noise at the transmitter, and then this is given to the receiver. So this is a model that we are going to use in our analysis. Okay, so you are modeling this addition right at the input of the receiver. So therefore this is called additive noise. There are certain noise which are in multiplicative nature, but here we are considering additive noise. Majority of the noise are in additive nature. So the next block diagram is the receiver, right? The final block diagram. Again, the receiver is a generic receiver. It can be an AM receiver, envelope detector, or synchronous demodulator for DSBSA modulation, or it could be phase locked loop or frequency compressive feedback system, frequency discriminator, or anything. And also the receiver may contain some front end filtering that you want to do to reject other signals, and many signals are coming in and you just like to tuning of the signal of interest, because if you have FM receiver, the frequency range is 88, as I said, 88 to 108 megahertz, but we don't want all this range. We want to particularly receive only one channel, so in that case we need to reject all other guys. So you use tuning of the tuning filter which reject all other signals, and it passes only the signal of interest. And the receiver, it could include some demodulation. So when I say receiver means it can have many things comprising in it. Okay, it could include in fact some de-emphasis filter, etc. So one of the main function of the receiver, of course, is to do the demodulation. Okay, that is the main function, but not only demodulation, it has also limit the amount of noise. One of the main function of the receiver is to limit the amount of noise that finally gets through the output. If it doesn't limit the amount of noise, then your system performance will go very badly. Okay, so the signal should go through very nicely without any distortion. And moreover, the main job of your one more main job of your receiver is that the noise should get attenuated as much as possible. So it should give more attenuation for the noise. So this is a typical, okay, this is typically done through presence of suitable filters in the receiver. So this is the overall block diagram in which we will concentrate. Now let us introduce some parameters. Okay, so the transmitter output has some power, and that power, let me denote by capital S suffix capital T, transmitter power. Transmitter power, because our performance will be in terms of what you call signal to noise ratio, signal power divided by the noise power, okay, finally at the output of the system. So that is why we need to know what is the transmitter power, and we like to talk in terms of signal powers and noise powers, and S suffix T is the amount of power that is being transmitted by the transmitter. The most important parameter which are of interest are input to the receiver, okay, how much amount of power is given to the receiver. So the entire amount of power that is transmitted is not received at the receiver. Why? Because in between you have channel, the channel will attenuate the signal strength, okay, because there is a lot of attenuation taking place in the channel. So finally what you receive is some power, let us say S suffix I at the input of the receiver. So S suffix I is the power at the input of the receiver. So obviously your SI is less than ST. Suppose if you transmit 10 watts here, maybe you will receive some 1 watts like that. Okay, so and the second thing is, let us talk about the noise power at the input to the receiver. So at the input to the receiver, let me write down the noise power by, maybe I will clear this figure to write down. I need some space. let me denote the noise power as n suffix I, input noise power, n suffix I, input noise power, and the suffix I denotes input, I input, and here also I have I, and that I indicates input power to the receiver. Okay, the subscript I here stands for input to the receiver. The signal power at the output of the receiver is S0. See, this is my receiver. At the output my signal power is S0 and my noise power is N0. Okay, S0 and N0. Output signal power and N0 output noise power. That's it. And again this O indicates output. The subscript O indicates output. Therefore, if you look at the figure, at this point, what are the components do you have? Here you have signal component, let's say Si of t, plus the noise is getting added, right? Therefore, n suffix I of t. Input signal component and the noise component. And this signal component has power capital S suffix I, plus the noise component Ni of t has power n suffix I. Okay, the noise component has a power capital N suffix I. Similarly, the output of the receiver also contains S0 of t plus n suffix naught of t. Okay, therefore, the output of the receiver also consists of the desired signal component and the noise component. What is S0 of t? Desired signal component. What is the desired signal component for my FM system? My message signal, both AM and FM, the desired component is M of t. Therefore, output of my receiver is M of t. If the receiver was perfect, the noise will be completely eliminated. Suppose if you have a very good receiver, ideal receiver, then this noise component should be 0. Okay, but you can never design such a perfect receiver. And the second parameter that we are interested is figure of merit, okay, which is very important for us. Okay, so it relates the value of your signal power, output signal power, and the noise power. So something called a figure of merit, and that is output signal power output divided by output noise power, the output signal to noise power ratio. Okay, when I say output, I mean at the output of the receiver. Okay, so this is what we are interested in. It's very important. Now this is called a figure of merit for a communication system. Figure of merit for a communication system. So just to give you a feel for what kind of signal to noise power ratios are useful, or typically the required values in various applications, I am going to give some typical values. For example, you take voice signal. For voice signal, the typical signal to noise ratio will be 5 to 10 dB. If signal to noise ratio S0 by N0 is equal to 5 to 10 dB, you will find that the voice signal is barely intelligible. You can guess about, you can guess or make out something is being spoken, otherwise you cannot make. So these are some typical values, okay, which are given to make some feel for what kind of values are desirable finally. And typically telephone quality speech, for telephonic conversation, speech, the signal to noise ratio S0 over N0 is equal to 25 to 35 dB for telephonic signals. And the third one is for good quality of broadcast signal, SNR is in the range of 45 to 55 dB. Broadcast quality, it will be 45 to 55 dB. And the fourth one is for television. Television, again this is going to be 45 to 55 dB. Okay. For example, if I say S0 by N0 is equal to 10 dB, what does it mean? The signal is 10 times stronger than what? Than the noise. If I say signal to noise ratio is 20 dB, what does it mean? What does it mean? Your S0 is stronger than N0 by how many times? 20 dB. 20 dB means 100 times. 40 dB means 10,000 times. 30 dB means 1000 times. So these are the intuition. These are the explanation of your dB. So these figures give you a feel for the kind of signal to noise ratio which will be acceptable in various applications. So now, keeping that in the back of your mind, let us start with how do we calculate output SNR in terms of the input SNR. Okay. Now let us start with a very simple communication system, that is baseband communication system. Baseband communication system. So in baseband communication system, what do I mean is, we do not carry out a modulation process or do not carry out a frequency translation. So that's what we mean by baseband communication system. Basically, we take the signal itself and transmit it as such without any modulation. You put a mic and take the signal, put an amplifier, and then put in the channel and then give it to the receiver. Okay, maybe the receiver output is, again you put an amplifier in the receiver. Receiver, you put an amplifier because the signal is attenuated by the channel, that's why you put an amplifier, maybe power amplifier and certain types of filters. Maybe you can have some filter, we don't know, filter, and here also you put some filter or something, and then finally give it to the speaker. So this is the typical block diagram of your baseband communication system. You notice here there is no modulation at the receiver, at the transmitter, no modulation at the transmitter, and no demodulation at the receiver. No demodulation at the receiver. So that's what we mean by baseband communication system. Like this channel is like a pair of copper wires. For example, your telephone line. Okay, so a pair of copper wires connects home to telephone exchange office. Okay, basically we are saying transmission without modulation. It could be a pair of wires, it could be a coaxial cables, but these will be short haul links, not for very long distance. This is for short haul links. HAUL, Hall. So if you want to transmit over a longer distance, typically multiple signals are have to be transmitted, and in that case we need modulation. For example, if you want to transmit from Chennai to Bangalore, then you cannot use a single pair of wire for each user, so that is quite expensive. In that case you go for modulation. Okay, here we use passband communication for longer distance, and this one is, let's say, around 350 kilometers, and this one is called long haul communication. So in long haul communication we employ modulation, but in baseband communication, that is used for short haul links, there we will not employ this modulation demodulation business. Okay, so over a short haul links or between one user and exchange, this is the kind of situation. So it's really a very simple analysis. Okay, the argument will be more or less directly valid for modulation system. So whatever we are doing the analysis for our baseband communication systems, that can be easily extended to our passband communication system also. So let us try to look at it carefully. So the reason why we want to do baseband system is because, other than the simplicity that is associated with the analysis, it will serve as a benchmark. Baseband communication system analysis serves as a benchmark, okay, to compare all other systems. So if you have modulation and if you don't have modulation, how will you compare each other, right? So you will have a modulation system like a DSP-SC, then SSP, then AM systems, then VSB, then FM, then PM. So I need to compare all these guys. How can I compare these guys? With whom should I compare? Okay, see, I have different modulation schemes, linear and non-linear modulation schemes, no problem. Then on what basis or with whom should I compare these modulation schemes? So what I will do is, I will take a baseband system without modulation, and then I will do the comparison. So how far my modulated system is better than my baseband system without modulation. Therefore, the analysis of baseband communication system is very, very important. So this is the relevant question we will try to address in this lecture. So how do you compare that? Okay, now let us give the model. See, your baseband system, as I said, you have transmitter and then channel, then you have the noise N of T, and then you have the receiver. When I say transmitter, then it has a pre-emphasis filter, as I said, and then it has a modulator, then it has a power amplifier, it has an antenna, then it may have some kind of band pass filter or something else, many things. Channel means, as I said, okay, pair of copper wire, coaxial cable and all those things, no need to write down here. And when I say receiver, again you can have a receiving antenna, then you have RF amplifier, you can have mixer, then local oscillator, then IF amplifier, before that you have a filter, right, and then IF amplifier, then pre-amplifier, power amplifier, and so on and so forth. These all are put together in this receiver block. Similarly, these all guys are put inside the block. Okay, now this I will model this transmitter. Let me model by a filter. That filter let me denote by hp of omega, and the channel again let me model by hc of omega, some kind of filter operation, and then noise is getting added here, n of t, and in the receiver let me denote by hd of omega. Okay, in the baseband communication there is no modulation. Okay, so this modulator is not there, and here also there is no demodulator local also, these are all are not there in the baseband communication system. Okay, so we said there is no modulation in the baseband communication system. It doesn't mean that we don't do any processing whatsoever. Okay, so in most general situation you have some kind of filtering at the transmitter itself. Even if you take your telephone line from your home to your exchange, it has some simple filtering mechanism, otherwise lot of noise will come and the signal quality will be degraded. So at the transmitter block is designed as a filter. So we modeled this transmitter block as a filter. Similarly, the receiver is also modeled as a filter. Okay, I simply put, okay, just an example. Okay, this is not, don't take it very seriously. Just an example, I put a HP of omega, pre-emphasis filter. Similarly, you could have de-emphasis filter in the receiver in the baseband systems. So some frequency components you may want to enhance at the receiver, and the corresponding frequency components you may want to de-emphasis at the receiver. So as I already told you, emphasis means you are amplifying the higher frequency component at the transmitter and attenuating the higher frequency components at the receiver to overcome the distortions, single tone distortion, single tone interference. So in this particular case, the transmitter either contains the filter or doesn't have the filter, no problem. Even you can say there is no filter, and the receiver also can say there is no filter. It's up to your choice. So in baseband system, just amplify the signal and have a sufficient power in it, that's it. So instead of this you can say some power amplifier. Okay, and then give to the channel. The channel is again modeled by hc of omega, then the noise, and then put another again power amplifier. That's it. So that is the only process you are doing, no modulation. Okay, so therefore you get the reasonable strength of the signal at the transmitter by employing the power amplifier. So now let us write down your hc of omega is the channel transfer function. As I said, the channel is modeled as a filter. Why is it modeled as a filter? Suppose you pass it through the filter, what happens? Then certain frequency, let us say if you take low pass filter, certain frequency components will be amplified and certain frequency component will be attenuated, right? That's what your low pass filter is doing. Similarly, if you pass pass it through a band pass filter, then certain frequency, the band pass filter response will be like this, centered frequency f naught. So certain frequency component in this region is passed and remaining frequencies are rejected. Here these frequencies are rejected, shown in the yellow color. So this is the job of your filter. By the same way, your channel also behaves differently for a different range of frequency component. For example, if you take a pair of copper wire, it behaves in one way for low frequency and it behaves in another way for high frequency. Similarly, if you take coaxial cable, it behaves for low frequency in one way, for high frequency in another way. So what I am saying, low and high, it is some kind of comparative term. Okay, it's not quantitative term, it's qualitatively I am saying. So if you use a pre-emphasis filter, then you must use a de-emphasis filter, because it should eliminate what we call out of band noise. So the next one is hp of omega, that is pre-emphasis filter transfer function. Okay, so limit the spectrum to a given bandwidth. So the main purpose of this filter could be to limit the transmission spectrum. So if you try to eliminate noise which lies in the same bandwidth of the signal, then it will also try to eliminate the signal also. So basically you try to eliminate the noise which is outside of your band. Let's say this is my band minus B2 plus B for my message signal. Now the noise is everywhere. See, the noise is here like this and like this, like this. Now what you can do is you can eliminate this noise, the noise which lies greater than F, the noise which lies less than F, but you cannot eliminate this noise. Okay, you cannot eliminate. Why we cannot eliminate? Because the noise is mixed with my signal. If you try to eliminate this guy, then this signal component also will be eliminated. Okay, so one cannot eliminate the noise within the band. So within this band 2B, you cannot eliminate. But out of band noise you can eliminate. In this range you can eliminate, you can remove. It can be removed, and in this range also it can be removed. No matter what you can do in this range, you cannot remove. You cannot remove the noise. So basically the only thing that we can really do is eliminate the out of band noise. This noise is called out of band noise. Why is it called out of band noise? Because it is lying outside of your band, your signal bandwidth. So that's what the receiver is doing now. So our input is a message signal M of t. So M of t also have some kind of model. So we will model M of t. So modeling of M of t. So actual signal of interest which carries some information, it must reasonably be random. Okay, for example, if you take speech signal or voice signal or music signal or picture signal, these all are a random signal. Okay, so because you don't want to transmit something which is precisely known to the receiver. See, already the receiver knows the information, then what is the purpose of transmitting it? So generally the communication occurs when the second party doesn't know about what you are going to speak, right? So that's what your whole information theory talks about, like information content of the message signal. If the message occurs with a probability 1, that means it is an sure event. In that case, what is the purpose of transmitting this? Because that message contains 0 information. Okay, if the message signal occurs with very less probability, that means it contains a lot of information. So here M of t is modeled. M of t is modeled as zero mean void sense stationary process. Void sense stationary process. So in short form, this is called WSS, void sense stationary. And this M of t is band limited to B hertz. For example, if you take voice, B equal to 4 kilohertz. In the case of frequency modulation, it is 15 kilohertz. B is equal to 4 kilohertz for telephonic signal. Okay, telephonic communication, and B is equal to 15 kilohertz for music and other signals. Now the power spectrum of WSS process is limited between minus B and plus B. So power spectrum of message M of t is limited to 0 to B hertz. Okay, here I am talking about power spectrum. Okay, so we are talking in terms of we are not talking in terms of spectrum of the signal. Instead of that, we are talking in terms of the power spectrum. Okay, so the random signal and a random process is always talked in terms of power spectrum. In case of deterministic signal, then we will talk in terms of spectrum. Okay. So let us assume we don't have any pre-emphasis and de-emphasis filters, but these are replaced by an ideal filters. So in this case, what I am saying is we don't have this pre-emphasis filters and de-emphasis filters. Okay. So let us replace this pre-emphasis filter by an ideal low pass filter. So what I am saying is your HP of omega pre-emphasis filter replace by an ideal low pass filter. Similarly, replace this HD of omega, because we are assuming that there is no pre-emphasis filter and a de-emphasis filter. Therefore, this you replace by an ideal low pass filter. Ideal low pass filter means it will not disturb the signal, so it will pass it as through it is. Now, how about the channel HC of omega? Most of the calculations for the purpose, for the practical purpose, like the purpose of signal to noise ratio analysis, we will assume that the channel is ideal. Okay, so here this channel is we assumed as ideal channel. So what is the characteristics of an ideal channel? Its amplitude is what? Constant, right? And phase is amplitude response is constant over the bandwidth of interest, and phase response is linear. So this we discussed in the beginning of the course. So ideal means, what is the meaning of ideal? Distortionless channel. There is no distortion introduced by the channel. That's it. So it will be ideal low pass filter. So therefore this HC of omega also will be replaced by ideal low pass filter. HC of omega ideal low pass filter. Okay. So it will have zero phase characteristics or linear phase characteristics. So HC of omega, HP of omega and HD of omega all are being modeled as low pass filter. Okay. So why are we doing this kind of modeling? Because we are saying that there is no modulation. Okay. So we are saying that the only effect of the channel that we are interested in is studying at this moment is the effect of noise. So we are concentrated only about noise. So that's why we are idealizing everything. So we idealized the transmitter filter, we idealized the receiver filter, and we idealized the channel. So let us look at the effect of noise. Noise modeling. How do we model the noise? Before that, I forgot to draw the figure. When I say ideal channel, then the magnitude spectrum is constant, minus B2 plus B. I don't expect the channel to be constant for the entire frequency band from minus infinity to plus infinity. In fact, I don't want. Okay, as long as my channel behaves very well from this band, then I am quite happy. Okay, I don't mind how my channel is going to behave out of my bandwidth. I don't bother about that. So my only primary concern is whether my channel is good in this band minus B2 plus B. That's it. So it is constant, no problem. Just go ahead. And it is linear. I'm sorry. It passes a zero line like that. The phase is linear. That's all. Okay. When I say ideal low pass filter, that means the low pass filter should have this kind of characteristics, this kind of transfer function. So constant between minus B2 plus B and 0 outside. So this is the amplitude characteristics, and phase response could be either 0 or a linear function like this, linear function. Again, it has to be linear over the bandwidth of interest. Okay, you have certain signal input power. Okay, so that's it. Now let us consider the noise part. Okay, so you have n of t. The output of my channel is n of t, and this one is given to the receiver, right? And here you have certain SI. Okay, so in this point I have certain input signal power. Okay, and the signal has a bandwidth of B hertz because it is after all a message signal without modulation. Now we need to find out what is the signal output power here in this location, output S0. The receiver is again modeled as ideal low pass filter with the bandwidth. It is a ideal low pass filter with bandwidth B hertz. So will there be any difference between SI and S0? No, because it passes as it is. So the output signal is the same as the input signal. Because my input signal SI has the bandwidth of minus B2 plus B, my low pass filter provides a unity gain between minus B2 plus B. So it is neither amplifying nor attenuating. Therefore, the input power is the same as output power. Okay, because the input signal has a power spectrum which extends up to B hertz in the positive side and minus B hertz in the negative side. Similarly, the ideal filter also has constant amplitude from minus B to plus B. So that's why the output power is the same as the input power. The spectrum is not disturbed. Okay, so this is my HD of omega, receive de-emphasis filter or receiver filter. And this HD of omega we assumed ideal filter. That means which doesn't do anything to the spectrum. So if it is ideal means it will not disturb as long as it lies between B hertz, 0 to B hertz and minus B to 0 hertz. So basically you see the same thing at the output of your receiver. Okay, so it looks the perfect thing. So in this case your S0 is equal to Si. What is S0? Output signal power. And what is Si? Input signal power. So output signal power S0 would be the same as the input signal power Si. So it is clear for this case that S0 is equal to Si. Okay, because in this case S0 of t is equal to Si of t. So this S0 of t is equal to Si of t implies that the output signal power will be the same as the input signal power or signal power input to the receiver. Now as I said, noise power, right? So what can you say about noise, right? So next we will talk about noise power. What can you say about the noise power? So you have N of t and this one is a receiver and this is my output. Here I have S0 and N0. Now input is my Si and Ni. Already we have done this Si part and S0 part. These two are over now. Now let us try to calculate this Ni part, input noise power and output noise power. Now what can we say about the noise power that will come out of the receiver? To do that we have to make some assumption regarding the noise power spectrum. Noise power spectrum. So how the noise power spectrum is modeled mathematically. Okay, so let's talk about the modeling of the noise. Before we talk about the noise power spectrum, we need a modeling of the noise. how do we model the noise. Okay. So what kind of model is more appropriate for noise? First of all, it is reasonable to say that it is zero mean wide sense stationary process. The noise process is zero mean wide sense stationary process. Okay, so in the random process course we explained why this is called a zero mean wide sense stationary random process. Okay, so therefore this is just like the signal m of t. In addition, we can usually assume that it is Gaussian noise. Okay, so therefore the noise is modeled as zero mean Gaussian noise. So although Gaussianity is not central to our discussion, as long as it is wide sense stationary, we will anyway work with the first two moments. Okay, the two moments are enough to describe its characteristics. Okay, so these two moments helps us to keep in mind that if it is a Gaussian process, the first two moments completes the description anyway, because if you take your Gaussian density function 1 by sigma times root of 2 pi e to the minus of x minus mu the whole square divided by 2 sigma square. So in this density function I need only two parameters, one is sigma square, another one is mu, mean and variance, that is enough. Okay, so in general it could have any arbitrary power spectrum. So therefore the power spectral density of the noise is denoted by S suffix n small n of f, and the small n indicates noise. The subscript n indicates noise. Therefore let us say the power spectral density function is denoted by S suffix n of f. This S suffix n of f is equal to n by 2, where the frequency is mod of f is less than infinity. That means what? You have the constant power spectral density right from minus infinity to plus infinity. Its magnitude is constant. The noise has equal contribution for all the frequencies. Okay, that contribution is n naught by 2. Whether you talk about a 0, that is a DC signal, 0 hertz means DC signal, or you talk about 1 hertz, or let's talk about 1000 hertz, or 1 megahertz, or 1 gigahertz, it doesn't matter, it gives equal contribution. Okay, so usually, in fact most of the time we will work with this model. Okay, this model we will consider. Okay, so if you recall from our random process course that I said that the kind of noise that we deal in communication system, or the kind of noises that we deal in communication systems are thermal noise, short noise, etc. Right? Recall all those things. So these all noises are modeled as a very wide spectrum range. See, the spectrum is very, very wide. Very, very wide. Its spectrum is very, very wide. Therefore, for all practical purposes, the noise can be considered to be a white noise process. White noise process. Okay, why is it called white noise process? Because the white light contains all its color, right? Similarly, here also the power spectral density is equal for all other frequencies. It contains all the frequencies. So generally it is called white noise process. Therefore, this Sn of f is usually equal to n naught by 2 and a constant power spectral density function. Okay, so what is this n naught by 2? Constant power spectral density function. And let's say some value n by 2. Okay, we already used the notation n naught. What is n naught? N naught is the output noise power, don't confuse. Okay, this n naught is different from your n. Okay, what is the unit of n here? This n naught is the power, right? Noise power. How do you measure noise power? In watts. Now in this case, what is the unit of this n? It is power density spectrum. Therefore this is watts per hertz. So let me summarize the unit. N naught is output noise power. What is the unit for this? Watts. What is n naught by 2? Power spectral density. Okay, power spectral density. What is the unit? Watts per hertz. So both are different, please don't get confused. Okay, n by 2 is a density function, therefore the unit is watts per hertz. When I say 0 mean, the mean of the process is 0 for all time. Okay, so where did I write 0 mean? Yeah, here I wrote, therefore it is mu suffix x of t is equal to 0 for all time value. Okay, that means the process mean value function is 0 for all time. Then it is satisfied its autocorrelation function, or equivalently I can specify the power spectral density function. When I say it is white, the power spectral density function is constant. Okay, so white means what do you mean by white? Where did I write? Yeah, white means what? Here white indicates constant. It has equal contribution, right, for all frequencies. That is why this is called a constant power spectral density. So if you have this kind of characteristics, like it has constant power spectral density and 0 mean random process, then its autocorrelation function, if you compute this, also we calculated in the random process course, will be an impulse function, or xx of tau is equal to n naught by 2 and del of tau. So given that the noise is wide sense Gaussian, wide sense stationary Gaussian, and has a power spectral density of power spectral density function Sn of f, what can we say about the noise power at the output of the receiver? You have receiver and this is S suffix n of f. Okay, now what can we say about the output of noise power? So what we are saying is, at the input to the receiver we have a noise function n of t with the power spectral density S suffix n of f. Now what will be the input noise power? Input noise power n suffix I, which is equal to how much? And then the next question that we would like to ask is, how is the noise power related to the spectral density? Now let us calculate one by one. The area under the spectral density is the total noise power. Now the input noise power, it exists from minus infinity to plus infinity, right? This is my power spectral density function with value of n by 2, I'm sorry, with value of n by 2. It starts from minus infinity hertz and it goes up to all the way plus infinity hertz. This is my power spectral density function. What is my power? Power is equal to power spectral density function times its length. What is its length? 2 times infinity, total area. So therefore input noise power input noise power is equal to total area. The total area is, what is the height? Height is n by 2 and width is this total width. It is 2 times infinity, again it is infinity. Therefore input noise power is infinite watts. Okay, because the area under the spectral density is the total noise power. So if you assume it is a white noise process, what is the amount of noise present in the input? It is infinity. Now this noise is given to a receiver. As I said, the receiver is modeled as a low pass filter, ideal low pass filter. Its magnitude is 1 and it is minus B2 plus B. Right? Maybe I'll write down here. This is my Sn of f and it has constant value from minus infinity to plus infinity, and this point is n by 2. And this one is given to receiver with the ideal filter characteristics, ideal low pass filter, minus B2 plus B, and this amplitude, let's say 1, and it has 0 response beyond f, beyond B, and here also 0 B. Now multiply these two guys in the frequency domain. Okay, so how do you calculate the output noise power? To do that, first you must multiply the output power spectral density. So recall from our previous random process course, output power spectral density. If I know the output power spectral density, then I can calculate output power, right? So this is going to be input power spectral density function multiplied by magnitude of square of your HD of f. It is H suffix D, de-emphasis filter. And integrate this output power spectral density over the range. What is the range? Minus B2 plus B. Okay, let's say my S naught of f is equal to output power spectral density, or I can say Sn suffix O of f equal to Sn of f multiplied by mod of square of Hd of f. Therefore, the output noise process or the noise output power is denoted by N naught is equal to integral of your Sn naught of f, and the limit is minus B2 plus B and df. So this is minus B2 plus B Sn of f, then Hd of f magnitude square and df. Okay, so this is a power spectral density, and we said the power spectral density is an even function. Okay, and this guy also magnitude function, therefore this also even function. And also this magnitude, what is the magnitude value? 1, so 1 squared. So let us substitute these values. Since it is even, I can write 2 times 0 to B, and this Sn of f is n by 2 and Hd of f is 1 multiplied by 1 and df 1 squared. So this is 2 will get cancelled, n times of B, so nB hertz watts. This is my output power, output noise power. Okay, so you can intuitively see why it is NB, right? Intuitively, how can you explain this result? The input is like this, and this one is multiplied by the low pass filter like this. So this is my Sn of f, and this is Hd of f. In the frequency domain, you are multiplying. So in this place it is 0, and here also 0. So if we extend, then here also your function comes and goes like this, and goes like this. But here it is, what is the value? That will be n by 2, and this one is 1. If you multiply, then you will get the same function like this. So this is n by 2 minus b and plus b. What is the area of this? Width is 2b and the height is n by 2. So 2 get cancelled, therefore n times b. So this is my output noise power. That's it. So output has the same shape. So what is the total area of the output noise process? The area is NB. So it is intuitively obvious. So the output noise power is NB. And that is something that you have to work with or tolerate with. And you cannot do anything about this. Okay, you cannot reduce below this value. How can you reduce? If you reduce the bandwidth, then you will lose the message signal. You will lose your intelligence. Suppose if somebody wants to reduce the noise power, reduce the noise power. Okay, if you want to reduce the noise power, how will you do it? Either you should reduce N, or you can reduce B. Okay, but N cannot be reduced. That is a constant, right? It is giving constant value for all the frequencies, equal contribution over wide range of frequencies. Therefore, N cannot be reduced. In fact, you can reduce the N by keeping your electronic circuit under controlled temperature. Then there is a chance, maybe within 0 degree or sub-zero, then there is a chance, because the thermal agitation will not be there, and because of that the thermal motion of electrons will be arrested, and so that you can control the noise current, and noise power can be controlled. But anyway, at room temperature noise power cannot be controlled, so you cannot reduce. But you can say, okay, let me reduce the bandwidth. If you reduce the bandwidth, my intelligence is residing here. Okay, my intelligence is, my signal components are residing in this location. Okay, if I reduce the bandwidth like this, then what will happen? This portion will be cut off. Then I lose my signal. So that also not possible. So this NB is the minimum amount of noise power. So you cannot go below that. So this is a noise that will come through if you want your signal come through. Okay, if the signal has this much bandwidth, minus B2 plus B, therefore you have to have a filter with this much of bandwidth, You cannot have a filter with smaller than B hertz, I mean minus B2 plus B. Okay, in case if you have a filter like this is minus B and this is plus B, then what will happen? Your signal will get distorted, because higher frequency components are eliminated. Then a human voice will look like somebody else's voice. A donkey voice will be heard as a buffalo voice or something else, I don't know. Okay, so you should not choose a filter okay, so you should not choose a filter smaller than your bandwidth of the signal, because if you do that, the noise that you will get in will be the signal will be distorted. If you choose your bandwidth less than the signal's bandwidth, then signal will be distorted. Similarly, suppose let us say this is my minus B2 plus B. Now in case, okay, let me choose my filter, low pass filter like this, minus B2 plus B. Here my filter bandwidth is larger than signal bandwidth. Now what will happen? If I have the bandwidth from minus B to B, that is enough for me, that is sufficient. But if you choose a filter like that, then unnecessarily, because in this place you don't have message. Then why are you choosing the filter like this? If you choose like that, then what will happen? The noise component will come inside. So this is my noise component. In this area, my noise power. After all, noise power is the area, right? So this area indicates additional noise power. That means indirectly you are allowing more amount of noise. Okay, so the two conditions you should satisfy when you are designing a filter. It should have at least B hertz of bandwidth. If you go below that, then your signal will get distorted. If you choose your bandwidth of the low pass filter is larger than your bandwidth of your message signal, then essentially you are allowing more amount of noise. Okay, and as I said, NB is the minimum amount of noise that you have to tolerate at the output of the receiver. So when the bandwidth of the filter is larger than the bandwidth of your message signal, then you are allowing the more amount of noise. Okay, if you do that, the noise that you will get in the noise that you will get in will be larger. Okay, so that's it. Now what is the signal output signal power? SI. And what is the output noise power? NB. Just now we have calculated this. Now let us try to calculate the output signal power divided by output noise power. It is going to be SI by NB. This is the figure of merit. Okay, and this is for SNR of baseband communication system. So we should always remember this by heart. Why? Because with this guy only we are going to compare all other modulated systems like a DSBSC system. With this we are going to compare DSBSC, AM systems, SSB, VSB and FM. All other systems are compared with this baseband communication system. When I say baseband, that means no modulation, without modulation. Okay, so we consider the bandwidth is 2B in the sense of mathematically. Okay, mathematically you can ask me, see, my message signal is bandwidth is B, then why are you calculating minus B? This I already told you many times. Okay, so in the conventional sense or real sense, the bandwidth is B hertz, but mathematical sense it is the bandwidth is the whole thing, negative frequency also included, so 2B hertz. So remember that. So therefore this is the benchmark. This is the benchmark of my communication system to compare the other communication systems. Okay, so benchmark in the system, in the sense, then we cannot have in any system a SNR which is better than this. So no matter what you do, you cannot have a system which performs better than this your baseband communication system. And assuming the noise power spectral density is n by 2. And this benchmark let us call by a special symbol called gamma. Okay, it is denoted by a lattice notation gamma. So therefore gamma is equal to SI divided by NB. That's it. This is the SNR of your baseband communication. So anything else that we do in terms of this benchmark. That is, we try to compare in terms of this benchmark with other systems. Okay. Now the one more point I would like to add in this connection, that is how can we express this S0 or SI in terms of your message signal M of t, because this is signal power, right? What is my signal? Message, right? So you have M of t. This M of t is given to HP of omega, pre-emphasis filter. Then it is given to the channel. The channel is modulus HC of omega, and then you have the noise N of t, and then at the receiver I had HD of omega. This is my receiver. So in this block diagram, we assumed everything is real, everything is ideal, okay, and we ignored the attenuation and we ignored the distortion, right? So if there is an attenuation, the attenuation factor will come in, okay, but here we assumed ideal. So finally, what is of important is what is the input power to the receiver. Okay, how do we calculate it? How do we calculate that? So now let us as I said, m of t is a noise signal. So this is given by m square bar. That means what? You square the signal and then you take the expectation of that. So this is going to be, this is the expression in the time domain. In the time domain I cannot calculate because it is a random signal. I don't have mathematical expression for my time domain signal because it is random. So in the frequency domain, if you take Fourier transform, how do you get this Fourier transform power spectral density? You find out the autocorrelation function. From the autocorrelation function, you take Fourier transform, you will get a power spectral density. Therefore, this is S suffix m of f. Here m indicates message. So 0 to B hertz. Why did I put 2 here? Because you are considering from minus B to plus B. Or you can put minus B to plus B, S m of f times df. Either we can calculate. What is my Sm of f? Power spectral density function of m message signal. Power spectral density function of the message signal. Okay, in the time domain I cannot directly calculate. In the time domain what you can do is you can calculate Rxx of t comma t plus tau. You take Fourier transform, you will get a S suffix m of f, and from this you can find out the power. Okay, in the time domain you cannot find the power. Therefore, the benchmark gamma is output SNR of whom? Baseband communication system. Okay, and this baseband communication system is S suffix I divided by NB. So this is the output SNR of baseband communication system. When I say this is the best thing one can do, here I am referring to linear systems. Okay, we find later that indeed modulation systems like FM and AM can do much better than this gamma. So how do we do better is something that will become later as we go along. So I shouldn't say that statement because we will simply say that this is the benchmark. So this is what the baseband system can do, and we will compare anything else with respect to this figure of merit. This is called a figure of merit. Okay, so let me stop at this point. In the next lecture, let us talk about AM system. Okay, the first one is DSBST system. So the performance of DSBST in the presence of noise, that we will discuss in the next lecture. So thank you very much.